Okay, hi. So many students have asked me about to re-explain line spectra during the consult. So I thought I might as well just record a video to explain this. So the line spectra that we have, we give you two types. One is the emission spectra, and one is the absorption spectra. If you have already understood this, then please don't waste time. Just skip this video. Okay, but if you have any doubts on how they are produced and what they are, you can stay along. So when you see this hot gas, this diagram, right? A hot gas passing through these jiggly lines, and then you get this emission spectra, right? How do you actually get them? So remember in the lab, right? We had this enrichment lab where we let you observe the emission spectra of a discharge lamp. So for example, I found this off the internet. We had the xenon lamp. Of course, in our lab, it was completely boxed up, right? It was a black rectangle box. But inside the rectangle box is basically this. Okay, this is a discharge lamp. Basically, high voltage electricity is passed across the ends, high potential difference. So electrons accelerate across, bump into the xenon, and excite the xenon. Right, so the xenon itself is now excited, high energy. Then you have this jiggly line, which is basically a diffraction grating. So do take note that in the lab, we give you this whole setup, right? And the diffraction grating is basically just this part in the middle. Okay, the whole thing is actually called the spectrometer. Right? This whole thing, including the lens to collimate the light coming in, so that it's parallel to hit this, and this thing will swivel around, right, at different angles to see. So it was like if you go straight through the piece should have been here. If you turn it down to this degree, right? If you remember that in the lab, you'll see at a different angle, right? So this is called a spectrometer, right? The one that's boxed in red. So don't confuse the two. So then if you place your eye here, you'll see different colored lights. Okay. So for example, if you have this colored light, right? I find the color as close to xenon light lamp as I can coming in, right? It's made up of more than just purple light. It's actually made up of a whole many different wavelengths of light. So for example, it has a blue light, right? Notice that it has a little bit off angle from the straight through, right? Orange is bent a little bit more. Then red is probably bent the most. I tried to choose the colors that we can find from this spectra. So why is that so? It's because of the diffraction grating formula d sine theta equals to n lambda. So essentially, as you move your eye, here, this eye, up and down, right, you will sometimes see a colored line when you're here. When you come lower, then in between the two, you'll see nothing. You come lower, you'll see an orange light. You come lower, you see nothing. Then you come lower, you see a red light. So basically, that explains this spectra. So what you see here in this spectra, this black background and colored lines, is essentially your eye moving across the different angles, right? And at the wrong angle, which may be around here, or not say the wrong, but at an angle where there's no wavelength, right, no light coming through, you see darkness, right? And at the correct angle, you get you see a wavelength of light. That means the discharge lamp xenon, right? The xenon discharge lamp has that component of wavelength in it, right? So that's how actually you detect an emission spectra. Okay. Next, is actually this question, right? You have a white light source coming in from the left, passing through a cool gas of a certain element, right? Then what is observed by the yellow smiley face, and what is observed by the blue smiley face. So this was an A-level question that was asked quite long ago, right? And I think even until now, many students have issues with this question. So I thought I might just as well record a video for this. So for those who know, right, and you guessed, right, the yellow smiley face sees the absorption spectra, and the blue smiley face sees the emission spectra. Right, one more time. Absorption and emission spectra. for the yellow and blue smiley faces respectively. So if you already know the answer, you can actually go. Don't waste your time. You can fast forward this to 2x. But if you don't know, then here the following is explanation. Right, so we can imagine white light. Right, we learn in primary or secondary school. There's a whole spectrum of light. So I'm just going to use a few colors to represent. So red, orange, yellow, green, dark green, blue, indigo, violet. I added one more because PowerPoint has those colors. Okay, so imagine that it has an equal amount. Let's say it is just completely arbitrary, right? It has 100 photons of each wavelength, let's say. Okay, and that's white light. So because this is a cool gas of a certain element, it will absorb certain wavelengths. So here I make the assumption that orange and green are absorbed. So if only orange and green are absorbed, the other colors are passed through, right? Are completely passed through, right? Transmitted. It's as if the gas wasn't there, right? Because all these wavelengths, right, doesn't interact with the gas at all. Because their energies don't feed the energy gap, right? Or the energy levels, the gap between the energy levels of this element. So all these are transmitted through. So then what is observed at the absorption on this side? Well, you will then see all colors except for orange and green, right? Red you'll see yellow, green, light blue, indigo, violet, right? Okay, so once the gas absorbs, right, this orange and green light is absorbed, they actually are re-emitted. Once they absorb, the energy must go somewhere, if not the gas will keep heating up, right? The energy is absorbed, is then re-emitted in all directions as given by these arrows here. Green photons also maybe in all the random directions. So if you notice, I was a bit cheeky lah, right? I just by luck draw two downward arrows here and two rightward arrow here just to show you. Okay, so in the two downward arrows here, right, the person here would then see, right, some of the original 100 photons, right? So maybe he will see 5 orange photons and 5 dark green photons, right? So what he see? This is therefore the emission spectra because he sees no other colors than the orange and the dark green photons, right? So he sees a orange and a green line. So he sees a dark background with colored lines. Okay. So here we also have a question, right? Something. If it's also redirected in the direction of the initial observer, the yellow smiley face, why do they not observe? Why do they still see dark lines here? It's because remember it's redirected. The 100 photons is redirected in all directions. So maybe he only sees 5. So 5 here is practically nothing, right? So this is what you call the noise effect, right? I mean, if your signals are so high, then this is like low, right? Then they can be ignored, right? Okay, yeah. So you essentially see a colored background with dark lines, right? The dark lines representing what was absorbed away. Okay, so I hope this helps. I hope this clears up any questions you have about emission absorption spectra. If I made any mistakes in this recording, please let me know immediately and I'll try to change this. Thank you.